Good afternoon. So I'm going to talk about, not directly about digitalization, which is really all about connecting your knowledge workers to the correct data and the tools to make inferences and take business decisions upon that data. But I'm going to talk about one of the two most important things that are barriers to successful digital transformation projects. One of the barriers have been discussed earlier, which is people's reluctance to change. There's a human factor to that. I'm not going to talk about that. I'm going to talk about another aspect that is oftentimes a problem, which is making the correct data available, making the complete data available. I'm going to talk a little bit about how you can go about doing that in a way that will increase the likelihood of success for your digital transformation projects. So what are some of the challenges that we're facing when we deal with the massive amounts of data that we increasingly are gathering? First of all, just finding the relevant data. Data exists many, many places. Data exists in many different vendor systems you're using. Every oil company uses a variety of different software vendor products, and they all have their own means of storing the data. You purchase data subscriptions from different data vendors, and you have documents. It might be stored in SharePoint, or might be stored in file systems around it. You also have problems. How do you qualify the data? How do you know the data you have is the most recent, correct version? How do you know it has a complete set of attributes and they've been validated? So you want to have some understanding that the data you're using for your analytics is the correct data. Also, getting data to where it needs to be. You might need to get the data into a data lake to facilitate analytics, which many companies have a major effort to do so. Or you may need to get into a specialized format to run a specific application. So it's not just finding the data, it's also getting the data into the application or making it accessible so it can be used. And then how do you keep it up to date? Data changes. You could be dealing with real-time streaming data, which obviously changes, or semi-static data that changes as your reservoir engineers or geoscientists are updating their interpretive work. And of course, on top of this, we're migrating from on-premise data and applications to cloud-hosted data and applications. And this is a transition. Most companies have a hybrid of both today. So that complicates all these things I've just described here. So what's the current state that exists in most companies for data? Well, different systems are used for data. So you might use vendor A's application suite and data storage for G&G applications. You might use a different vendor's suite of applications as data store for your engineering applications. And you may or may not have a well-defined master or system of record for different data types. You might just have working projects. And usually companies deal with unstructured data separately. Unstructured data being data like just reports in a PDF format or a Word format or a PowerPoint or email message. There's lots of valuable information in documents that's not structured. And where does that exist? It could be in file folders on a shared file system. It could be in SharePoint sites. It could be cataloged in a document management system. And most companies have no means of having a view across all this diverse data. In order to find data, they have to go into each separate system and use its tools for finding data. Some of those application suites might have good tools for helping you find data, others don't. So it's really it's a mixed situation for most companies. So I'm going to describe an architecture of an approach to make the data more readily accessible. And it consists of, on the bottom, you're seeing the different data sources I talked about earlier. Let's see, is this? Okay, I guess the pointer's not working. The lower half represents data, both structured and unstructured data. And on the top, we're showing some web-based interfaces. You need to make the data accessible to users. The user interface should have a look and feel more like Google Maps or Google Search than a geotechnical application. You want to make it as easy to find data as it is to buy something. My wife has no problem finding things on Amazon and executing a purchase in a matter of a minute or two. Why isn't it that easy for us to find data and get it into our application? There's no reason it couldn't be as simple as that. So we want to have a simple web interface that's accessible to anyone within the organization. And then what can you do within that interface? Well, you want to be able to view the data. And given the fact that much of our data is spatial, you want to be able to view the data in a map view. You want to be able to look at table listing of the data. You want to have some specialized visualization of the data for seismic data, log data, other some of our specialized technical data that generic visualization tools don't cope with. And then you want to be able to link to visualization tools. We already are displaying dashboards. Maybe you're already doing data analytics with Spotfire or Power BI or Tableau. And you want to be able to launch those visualizations connected to the data that you've already found and selected in the web user interface. What services are needed to enable this sort of infrastructure? I showed in here that in order to enable this view across all these data sources, you need to have a search engine. So on the far left, we talk about search engine. The search engine is populated by having what we call indexing jobs that are run within this microservice container. Indexing jobs crawl through the structured and unstructured data, extract attributes. So when you issue a query, your Google-like search, it's not having to go connect to every single data store. It's just going against the search index. That's the way that Google makes it possible for you to search across hundreds of millions of items across the internet. It's not executing the search in real time. It's indexed the data. We need to do the same thing for all of our EMP data so it become readily searchable. So that's the role of an indexing job, is to connect the data or documents, extract the relative data and put it into the search engine. Then you might want to have enrichment jobs. You might be indexing documents, and you might want to extract some structured information about the documents. Maybe you want to infer what the spatial location is of that report. Or maybe you want to extract the well name. Or maybe you want to extract the operator name. You can write enrichment jobs that add supplemental information or metadata to those documents to make them more relevant to help you search for it. We also have you want to have the ability to score the data, to assert quality metrics. So based upon business rules you establish, you can establish rules for what's considered to be the mandatory attributes. What are the allowable ranges of attributes? What are the relationships between things? You want to make sure that a well log isn't deeper than the TD of the well, for example. So those are all different types of rules that you might make, and you come up with a numeric score for all the different data types, so you can then track how your data quality changes over time. You might want to have data transfer jobs. When you find data from one source, you might want to select it and say, move it to another one. And that uses a data transfer job, and that just moves data from one source to a target and does the necessary transformation of the data. And that can be done either on demand or as a scheduled task to keep the data up to date. Other services you might help you to make this access to data more efficient is being alerted if data changes. You might want to register that to be notified if a new well is introduced in the area you're working in. Or if you're a reservoir engineer, you might want to be notified if the key horizons that your model is based upon have been updated by the geologist. So you might want to register to be notified of changes in data you're using or be notified of new data being available. And then you also want to be able to visualize, as I indicated up here, the specialized seismic data, well log data and all. So that involves something that might be called an entity service that serves up the data in a standard way, regardless what vendor system it's coming from. So that the visualization tools can be used to compare data coming from any of the different vendor systems you might use. So this is kind of an overall architecture for a solution to make access to data easier and make data more accessible to users. So how do you need to be able to deploy this? Well, as I alluded to earlier, most companies are somewhere along the line in their cloud journey, moving from on-premise to cloud. Probably not all the way in the cloud yet. So you might want the option of storing things on-premise where everything's installed on-premise, the data's on-premise, this back-end services are there, and your users are on-premise. Or you might be pure cloud. Maybe you've already moved all your data to the cloud, so you put all these services, the search service and everything else, up in the cloud, and it's able to serve to your users anyway in the network that have access to this. Or you may have a hybrid where you have a data agent on-premise, which is responsible for connecting to the on-premise data stores, the documents or the databases that exist on-premise, but then it is able to index into a search collection that's hosted in the cloud, and the cloud-based installation can also connect to cloud. So this way you can combine information coming from both cloud and on-premise securely. So just a little example, some case studies from a few different companies that have adopted this type of architecture. This is a case of a major oil company that had data across many different systems. They had data on-premise, and they had data in also hosted in cloud-based repositories from their data vendors. And they also had documents, tens and hundreds of millions of documents scattered across. They had many people retiring. So people who knew where to find things were gone. So they had a challenge of how they harvest this rich set of data they have. They know it's there, they don't know where it is and how to get it. So they implemented a solution along the lines what I just showed you earlier. And this is a screenshot without any proprietary data showing the different data and how it's presented in their user interface. They connected to 35 different data types, primarily emphasizing geology and geophysical items. You see that on the left. I'm not going to read all the data types. And over 24 different data sources, both cloud and on-premise. And I think they're up to about 350 or 400 million items that have been indexed. So they can go in now and type in a search term, Google-like search, and within a second find items that are there. So this solved the problem of how do you find things no matter where it's stored. And just to get a little bit of the numbers, they have over 20 million wells, 45 million well logs. So the same well might be in different systems. That's why they have so many. There aren't that many wells in the world, but they have the same well stored in different systems. This view gives them the ability to see where it is anywhere in any of their vendor systems. And the result is what used to take days to find data, maybe even weeks because you have to make requests to have other people do a search for you, now it takes minutes. So this is just an example of just connecting to the data adds value. Again, this then sets the stage for enabling some of the other sorts of things that digital transformation does. Another example, a national oil company that had merged different business units that had historically used different vendors' products and had different data management policies. And their headquarters had a mission to try to impose some more consistent data management policies and to elevate the importance of data quality and measuring data. So they wanted a mechanism of quantifying data quality and help them focus their data management activities. They had 12 different assets, different oil fields that they wanted to manage. They had data sitting in Petrel, OpenWorks, EDM, ProSource. They had their own corporate data stores. And most of the data that they wanted to look at were well and production related. So in this case, these are some examples. This is Spotfire visualizations that are put together that visualize the scored data that was in that search index I showed earlier. So this is a high-level dashboard with KPIs for the overall view of all the assets, accuracy, completeness, conformity, consistency, and uniqueness, all the different attributes of quality measurements. And it shows broken down by field, by data source type, and so they can slice and dice and see where their data is. And also there's a historic component of this so they can see how the data quality changes over time. This is kind of a management view of data quality. And this is what a data manager might use. They can drill down and look at distribution of scores, click on a given score bin range. Say, I want to look at the bad data that's showing 0 to 10 out of a score of 100 of completeness. Click there, and on the right, I blurred out the real data, but it shows you individual well records, individual well logs, individual seismic data records, and the highlighted red cells are where those attributes fail their rules. So it gives you the ability to, across tens of millions of data items, find individual ones that aren't compliant with your rule set. So that's one way of drilling down by score. They wanted to be able to drill down by rules. They want to find, here's a rule. Again, I blurred out some of it. I think the rule is that the well must have an operator name. So you could click on that rule and find all the items across your entire data enterprise that fail that rule. So again, you see the power of being able to connect to all the data. You can compare data across projects, find data that exists in one project and not the other, which is important. And the results now, the data managers have access to these quality metrics across all their data sources in one place, and they then can focus on efforts to improve the data quality. Last one, really quickly, is a company that was migrating their data to OSDU, a cloud-hosted vendor-neutral data platform, and they wanted tools to be able to view the data coming from OSDU and help to get data from the on-premise data to OSDU. And they leverage the same framework to connect to their on-premise data and transfer the entire contents of some of their studio repositories, well, seismic interpretation data, up into OSDU, and then be able to view inside the web-based interface data coming from both the on-premise data sources as well as OSDU, as well as accommodate some other data types to add to it. So I think you see there's a variety of use cases that could be accommodated by having a data integration framework that's vendor independent that ties to all these different systems and helps you set the stage for migrating your data to the cloud. So I'd like to thank you, and I'll stop here.